remember that when voltage is being generated, we call it EMF. And when voltage is being used up, we call it PD. So in this simple circuit here, the cell is the only thing that's generating any voltage. Let's say this cell is a 3-volt cell. That means it generates 3 volts. We say the EMF of the cell is 3 volts. Remember Kirchhoff's second law says that if you have a closed loop, and our simple circuit here is a closed loop, if you have a closed loop, then if you add up all of the voltage that's being generated and you add up all the voltage that's being used, those two numbers need to be the same. In our circuit here, we've got the total that's being provided to the circuit is 3 volts. So that means that our circuit must use 3 volts in total as well. Now, if you have resistance, you will use up voltage. We usually pretend that wires don't have any resistance, and we usually pretend that cells don't have any resistance as well. So if we're pretending that, that means that the wires don't use up any PD, the cell doesn't use up any PD, it's only the resistor and the bulb that are using up the PD. So between them, they need to use up 3 volts. So if we measured the PD across the resistor and we found that that was 1 volt, then we would be able to tell, we would know that the PD across the bulb had to be 2 volts because they're the only ones with any resistance, so they're the only ones using up any voltage, and between them they need to use up 3 volts. So if you have resistance, you will use up some of the voltage. Okay, we're now going to stop pretending that the cell has no resistance. To show that we are not pretending the cell has no resistance, we draw it differently with this dotted box around it, and we actually draw in we draw a resistor inside the box to show that we are treating the cell like it has resistance. We're going to keep pretending though that the wires don't have any resistance. Okay, I'm just going to highlight the stuff that we're pretending doesn't have any resistance. All right, so anything highlighted in yellow we're pretending has no resistance, which means that it doesn't use up any voltage. So it's just the resistor is going to use up some voltage and the cell is going to use up some voltage. So if we say the cell has an EMF of whatever, Kirchhoff's second law says that that total EMF has to equal the PD across the resistor plus the PD that's being used up by the cell. So let's call, should we say this, what PD, we'll call that the PD across the resistor, and this is the PD across the cell. Okay, now we know a formula for PD. It's V equals IR. So if we call, I'm going to go for a different colour. So if we say the resistance of this resistor is going to be big R and the resistance of that resistor is going to be little r, and we're going to stick a ammeter in that circuit so that we can measure the current. All right. So now we've got EMF equals, right, so the PD of the resistor is IR, and the PD across the cell, so that the voltage that the cell is using up is I little r, it's R. Okay, and if we want, we can then rearrange to get this. So you might see that sometimes, that arrangement. All it is saying that the EMF is equal to the PD that's used up by the outside circuit plus the PD that's used up by the cell itself. Okay, so we're going to think about the experiment now, and in the experiment you're going to have a variable resistor instead of a normal one, and you are going to measure the current, and you're also going to measure the PD across the resistor. Okay, so we're going to have a results table for current and resistor PD. And so you'll just measure and then change the resistance of the resistor, and that will give you a different current and a different PD reading. Change the resistance of the resistor again, different current, different PD reading, change the resistor, and so on. You're expecting a straight line, so you need 5 results or more. Okay, thinking back to our equation before, we said that the total EMF has to equal total PD, so the EMF has to equal the PD across the resistor plus the PD across the cell, so used up by the cell. Now we have actually measured the PD across the resistor. In our results table we called it V, and then we said that the V equals IR. So this V here is IR because the resistance of the cell is little r, and we actually measured I as well. So those are the things that we've measured. So we do a little bit of rearranging. I want to I'm going to move the IR to the other side, like that. And then I'm going to just write it in a different order. So now I'm going to have V is, I'm going to put the IR in front, and I'm going to put the R in front of the I, like that. This is all just rearranging. We measured the V, we measured the I. Okay, you are going to plot your voltage on the y-axis, and you're going to plot the current on the x-axis. And why are you going to do that? Because the form of this line is now, so if you're going to have this be the y and you're going to have this be the x, then y equals mx plus c. So your EMF, which is a constant, that's going to be the y-intercept. And the internal resistance of the cell is also a constant, and minus r, that is going to be the gradient. That's why you do it. So you will end up with a graph of V in volts times I amps, and you'll end up with something like this. And we're saying that the equation of that line, y equals mx plus c. On the y-axis, we've got the voltage. On the x-axis, we've got the current. What is multiplying the x is minus r, and what is added on at the end is the EMF of the cell. So that means that there's the y-intercept, that's the EMF of the cell. And then find the gradient. Notice it's a negative gradient, so let's say that this was 3 and this was minus 3 because it's going down, and 10. So the gradient of that line is minus 3 over 10, so that's minus 0.3 ohms because it's a resistance. Sorry, because it's V over I, and that gradient is equal to minus R. So that means that